Hello, I'm Florian Guitton from the Data Science Institute at the Imperial College of London. I'm here to present the paper I co-authored with my colleagues Axel, Oehmichen and Étienne Bossé, which we're presenting to the Data for Policy Conference 2024. The submission number is 172 and the title is Honest Computing, Achieving Demonstrable Data Lineage and Provenance for Driving Data and Process-Sensitive Policies. This is a work that we've been working on for a few years, which effectively attempts to try to find some technological solution to problems we see in the application and enforcement of regulatory frameworks today. I want to first go over some motivation for us to look at this particular piece of work. Today, in the modern landscape, we have two different types of approaches to drafting regulation. One is principle-based, the other one is rule-based. Principle-based regulation typically tend to favor qualitative measures in the definitions of terms and articles. For example, they will refer to the fairness of a process or the reasonableness of a decision. In contrast, rule-based regulation will typically tend to be more prescriptive, demonstrable, or reproducible. They will effectively say things like, it must be done within 72 hours, or it has to be done after 3 months. In effect, since the financial crisis of 2008, in the UK and to a lesser extent in the European Union, we have seen a progression of regulation moving towards more and more principle-based regulation. We'll see a bit how this can have a trickling down effect that can be problematic. Simultaneously, over the past decade and perhaps before, we've also seen a number of scandals meant to be prevented by those regulations. From the Barclays dark pool scandal of 2014, going through to the NHS deep mine scandal of 2021, and all the way up to more recently, in January 2024, when The Guardian revealed that TfL had been abusing data obtained through one of its partners about European drivers, that is post-Brexit. And we see that all of that has been marring the news landscape, despite regulations such as GDPR being in place, both in the European Union and in the UK. By no means does this apply exclusively in the European Union or in the UK, as other similar regulation also exist elsewhere. I want to also acknowledge that when we talk about regulation and that we talk about finding technological solution to regulatory problems, we hear a lot about the pacing problem, about the technology velocity. Between innovation and regulation, it's always been thoroughly discussed that they are oftentimes a fracture, where technology evolves much, much faster than regulation can be drafted to effectively apply to it. From financial technology all the way to genetically modified organisms in the food pipeline, or more recently, the applications of artificial intelligence and its development, from anything from the use of artificial intelligence decision-making in robot surgery or self-driving cars. We can see the divide in terms of the velocity. But occasionally, and this may have been the case for regulation like GDPR, the regulatory goals outpace quite significantly the capabilities of technology to address them, rendering rule-based regulation difficult to draft. And effectively, this is what we see with GDPR, a regulation that characteristically lacks any prescriptive mechanics for operating data safety or indeed the auditability pipeline. Effectively, GDPR today has no other choice but to create a punitive structure if found out, rather than enforce good practice and regulation from the get-go in a prescriptive fashion. But this may be changing, and we've seen that as well with the appearance on the scene of the Digital Operational Resilience Act, a regulation that is meant to be put in place in Europe from January 2025, next year, and that introduces some interesting wording more reminiscent of a rule-based approach to regulation. Very specifically, it defines that entities shall design, procure, and implement ICT security policies, procedures, and protocols that maintain high standard of availability, authenticity, integrity, confidentiality of data, whether at rest, in transit, or in use, and also apply well beyond the personal data scope that applies to the GDPR. And here you can perhaps start to understand some contrast and similarities between the two, effectively approaching the issue of availability in the same fashion, as well as the issue of authenticity and integrity validation, the correctness of the information, but then substantially changing when talking about the confidentiality of the data at rest, in transit, and more crucially, in use, something very difficult to achieve technologically thus far. To help in understanding how and why we came up with the structure for reference implementation of honest computing, it's important to understand a few concepts. For example, the concept of data provenance. Data provenance is about the origin and authenticity of data. It involves tracing data history and understanding for each of the data elements their origin, changes, and who is the author, for example, as well as any other action that would have been underwent by the data as it goes through a journey. However, it remains a bit of a discrete process, meaning discrete from a mathematical sense. Every single element of data provenance might not necessarily be connected to the other, and effectively you do end up with quite a patchy history. To sort that out, there is the concept of data lineage. Data lineage is similar in nature, obviously, but does not content with simply capturing the origin of the data and its changes, but effectively capture every part of the changes. Effectively, metadata objects and other related bits of data that were used within the original transformation. This could be code, this could be external data, effectively creating more of a hierarchy of dependencies in a fully continuous view of the data. Obviously, our work doesn't really start from nowhere. There's been significant amount of work already in terms of understanding how to use electronic data tracing and information in the context of regulation, and this is where you can find a lot of literature, for example, on digital evidences. However, up to very recently, and still today, it is judged in the literature that effectively leveraging cryptography and to authenticate the digital evidences, which is the most adopted workflow, remains complex and quite challenging. Equally, in designing our reference architecture and particularly moving towards an implementation, a first implementation of honest computing framework, we were very careful to consider the technological readiness level of the choices that we were making. A technological readiness level is effectively a scale that provides useful tools for understanding and judging of the maturity level of a particular piece of technology. In the context of our work, we have decided to only use technologies that reach, at the very least, technological readiness level 5. This effectively means that for our implementation phase and within the design of our specification for honest computing, we've only considered technologies that had been successfully tested outside of a lab environment, which means, for example, as part of pilot tests for certain types of application of the technologies, but not necessarily fully production-ready technologies. And so finally, this brings me to sort of honest computing and the requirement that we have baked into honest computing in order to achieve a higher degree of digital evidence, effectively addressing data provenance and data lineage. First of all, to properly understand the data lineage, we need to care about the deterministic aspect of data processing. Honest computing requires any processing of data to effectively be done deterministically. This will mean that the computer program that performs any computation on the data is effectively able to perform the computation consistently and robustly in a reproducible fashion. The same data in leads to the same data out. In real life, a lot of data processing can be influenced by things like the time on the clock or the amount of memory available to a computer, Or perhaps if the computer has multi-threading, the other processes that are being processed at the same time on the same machine. Another element important to honest computing is transparency. When software operates in opaque and proprietary ways in a sort of black box fashion, it's very difficult for us to understand the accountability of the computational process. Transparency in system really allows us to start building accountability and allow stakeholders or users to trace the decision-making process of a particular piece of technology. This doesn't necessarily mean that we are looking at fully open source, but it is certainly part of it. Eventually, we also need to get to verifiability. Verifiability is a pillar in honest computing for building policies specifically that can render computer system fully accountable. It allows checking the correctness and the reliability of a computation. Mechanisms such as attestation, for example, allow users of particular computer systems to be able to perform checks over whether or not the answers provided by a system was in context, validated and authentic with regard to the microchips that perform these computations. Finally, integrity is one of the most important parts as well. Sometimes we refer to this as tamper-proofness, and it applies to the data as well as the system. When we talk about the integrity of the data, we typically mean enforcing its accuracy over time and ensuring that it does not degrade. From old problems such as the bit rot, all the way to checksum mechanics that we can adopt in more modern systems, it is an important part of integrity. The second aspect is the integrity of the system that is performing the computation. And that can be through software level, such as the application of firewalls to avoid the loss of integrity due to some malware infection, but also the physical integrity, make sure that the system doesn't get on fire in the middle of a data center, for example. Important to note when we talk about tamper-proofness in integrity, that in the context of computing and technology, we often refer to the concept of tamper-proofness as tamper-evident rather than tamper-resistant. Perhaps naturally from those two concepts, you can understand the nuances in the definition. It is not the goal for a computer system that performs integrity or enforces integrity to necessarily be infallible. It is just a feature that we mean that as soon as there is a change, then you would be able to know that there has been a change. In our paper, or to come up with our new framework for honest computing, we've considered the threat model of typical modern systems. And we've kind of boiled it down to a few key things that need to be understood in order to properly comprehend the usefulness of secure honest computing. One is the difference that there is between secure computing and honest computing. In a lot of modern systems, and perhaps in a lot of marketing material, you'll hear that a system is secure for this reason or that reason. And security is important, but does not apply honesty. While a secure computing system aims to protect the system from making errors or from being accessed to unauthorized access was disrupted in any other way, it doesn't necessarily inherently mean that it ensures the honesty or the transparency of that system. You may have, for example, a system that contains a database, and that database contains data that is encrypted when it's at rest. However, the system is not able to really tell you necessarily whether or not the administrator of the system has been able to obtain the data on its way to the database before it was encrypted, or perhaps after it was decrypted through the transit and before it was encrypted for rest. Going back to this key issue of data in use. Finally, we ended up pinpointing the problem. And perhaps you've heard of the concept of trustless computing, and this is very, very much linked to honest computing here. The problem at the end of the day is trust. Trust, in effect, is rather dynamic. It's a belief-based system rather than a deterministic set of rules that are evidence-based and allow reproducibility and mathematical validation of a claim. When we talk about the accountability of a system, we must make sure that we do not trust the system. In fact, trust in the context of honesty is the enemy. In computer systems, we typically tend to talk about a root of trust, meaning the starting point at which we have to start trusting the system. Root of trust exists in a wide different variety, from human root of trust, institutional root of trust in software, or indeed effectively root of trust in hardware. Obviously, the higher level of the root of trust you are, the greater the risk, the greater the failure surface, the attack surface. In practice, when we talk about things like GDPR, we put a lot of emphasis on the idea that you trust either the institution or the human that is performing a particular modification or particular data action. But this is not enough, and we argue in the context of achieving requirements for the DORA regulation that honest computing must be based to as low as possible a root of trust level. Effectively, in the context of our work, we are looking at hardware root of trust. And this is how we landed on a set of technologies, a set of key foundational technologies for honest computing. First and foremost, we have confidential computing. Confidential computing essentially is based on hardware called trusted execution environment that are Turing complete capable, meaning they can perform any computation. They effectively divide the processing power that they have into secure enclave in which applications can execute while protected from the outside world. Trusted execution environments are not all made equals, and some of them do not provide the necessary features or capabilities that honest computing demands, specifically the ability to provide integrity, freshness, encryption, and most importantly, remote attestation. In the paper, we go into more detail as to each of these different features and why they're important, but it is important to consider that not all TEs are made equal. To sort out the issue with regard to data availability, which is one of the key elements of the regulation, we also think in terms of distributed ledger technologies. Perhaps you'll be familiar with this term, as it has often been used over the past few years in the context of decentralized digital currencies or cryptocurrencies. Effectively, at its core, digital ledger technologies are databases that maintain continuously growing lists of records that are linked together through cryptography. For honest computing, we typically want to move away from proof of work and proof of stake, which are techniques used in game theory to be able to create the necessary structures for distributed ledgers to function, and prefer other alternatives. There are various reasons for that, but among other things, we would want to care about the flexibility, the speed, and also perhaps the energy footprint that those game theory-based systems unfortunately incur. Therefore, we would typically suggest, with regard to our specification, that an implementer of honest computing system use a proof of processor, otherwise called as a proof of authenticity, perhaps based on a Byzantine fault-tolerant Raft implementation. And this will effectively ensure low cost, very high speed, flexible scalability, and a much, much smaller energy footprint with the same cryptographic guarantees at the level of the distributed ledger. Perhaps from the distributed ledger technology use, you will have understood that consensus decision-making in honest computing system are very important. In fact, as part of honest computing, we do consider multi-level consensus. And this is because addressing decision trees at every level of the system remains important. Beyond the use of the DLT, the process layer that in which the application effectively executes needs to feature consensus algorithms. Either because it needs to protect a particular piece of private data, such as encryption private keys, from being very easily obtainable by spreading it effectively across multiple machines, multiple node, details of that in our paper, but also in terms of the human-driven actions. When specific decisions have to be taken with regard to a confidential computing process or an honest computing process, you may need a multi-stage human-driven process to achieve that, and cryptography here with multi-level consensus can help you. There are additional considerations that we look at in our work. For example, we explore the idea of using homomorphic encryption, which is a cryptography technique that allows the computation to be performed on encrypted data and for the result to remain encrypted throughout the life of the data. Something that can complement honest computing systems that require decryption. There's also the topic of differential privacy, which is a set of techniques that apply in the field of data privacy, where you have the ability to obfuscate the result of certain queries in a predictable fashion to make sure that you protect data against leakage for individual data points. Post-quantum cryptography is something that we also talk about in our paper, looking specifically at defense mechanism against new types of system, which are potentially, although not necessarily provably, able to break the traditional classic encryption more easily. Additionally to those, I can think as well about HSMs, which are hardware security modules, effectively known for their tamper-proofness. They're already an industry standard in the insurance of private keys for encryption, and this can be a good complement to an honest computing system that is more flexible. But at the end, we also acknowledge, as part of our work, that there is a need to combat poor software practices. While honest computing systems can achieve very high level of privacy and confidentiality while providing all of the necessary cryptography guarantees of data execution and processing, it cannot be substituted for correct software hygiene. Indeed, the applications running in the trusted execution environments are human written, and software designed with features permitting data extraction must be carefully considered. Data extraction, do not get me wrong, is necessary, particularly, for example, in the context of a forensic analysis or indeed in case of legal proceedings. However, it needs to be very well understood and well audited as part of an honest computing system to be able to keep on adhering to those principles. And the applications of honest computing are far between, are plenty. From healthcare to finance and banking, for example, with regard to the design of digital currencies that can be more flexible, more programmable, while at the same time alleviating some of the bigger problems that questions that have been raised in the context of those digital currencies, as well as trading, where the price discovery fairness can be adjusted when larger corporations are bidding against smaller players. Supply chain management is another area where lots of changes can be done, notarization also. And finally, perhaps more specifically, data access revocation, a holy grail of computer communication. If you think about it, as soon as you have released a piece of data for processing to a third party, in the context of the data processor, data owner, data controller relationship in GDPR, you will understand this. As soon as the data is out of the original system, it is effectively lost. The control of it is lost. It could be copied, it could be leaked out, it could be maintained. There is no oversight possible. Honest computing can perhaps finally provide that bridge, allowing the design of systems that can truly perform data access revocation. And with that, I will invite you to consult the paper to get a bit more detail. We have already started work on a follow-up, which will be looking at the effective technical implementation of our honest computing framework. In the meantime, I hope you enjoy the rest of the Data for Policy Conference 2024, and I'll look forward to see you in more research. Bye-bye.